This is really high school.
They were almost a bit like that.
I gotta read it.
This is the most focused.
How are y'all? How are y'all in the back? How's it going? Do y'all have questions on the homework before we start?
10.314. I know we went over it, but I said it was 13 because I talked about this.
This one or 13?
Oh.
I don't know what console you use, but. Do you use Microsoft?
No, this is the same place.
So what do you play on?
Okay, so the deal with telescoping series is that you just need to write out some terms to see what cancels. You need to go out to the nth term because we need to find the nth partial sum. And then we're taking the limit on the nth partial sum. So just as a reminder as well, any series that you can find a formula for the nth partial sum and evaluate the limit at infinity, you can evaluate the sum of an infinite series that way. So we'll just write some of these terms out. When k equals 1, k equals 2, k equals 3 maybe. I'm not sure how far we should go out. We'll just start there, see if we get any cancellations. So when k equals 1, we have 5 over root 5. Minus 5 over root 7. Yeah, 2 apart. K equals to 2. 5 over root 6 minus 5 over root 8. 5 over root 7 minus 5 over root 9. Okay, so we get cancellation there with minus 5 over root 7, 5 over root 7. So that's enough to tell us what cancels, right? And let's just go ahead and look at the tail. Again, stopping when k is equal to n. So the previous k equals n minus 1, k equals n minus 2. It's really up to you how many you need to look, or the series rather, how many you actually need to look at. It's up to you as to how many you want to look at. Okay, so when k is n minus 2, we have 5 over square roots of n plus 2 minus 5 over square root n plus 4. K equals n minus 1.
How did you write that out?
What? This one?
Yeah.
So k is n minus 2, so that's the square root of k plus 4, where k is n minus 2. So n minus 2 plus 4. What were we doing? Oh, n minus 1 in there. That's n minus 1 plus 4. 5 over root n plus 3. Over n plus 5. And then k equals n. So we'll see here again, our assignment, we have this canceling with this. So I don't know how you think of that, but cancellation is by terms, or by pairs rather. The second in the pair cancels with the first, and that's what, 1, second to the right. And then similarly, the first term will cancels with the second, that's 2 to the left. So then we just look at all of our terms. Does the 5 over root 5 cancel with anything? No, because it cancels with the second term that's to the left. There's nothing to the left of this. So that stays. The 5 over root 6, does that cancel? No, again, 2 terms to the left. There's not a second term or pair to the left. That stays. The minus 5 over root 8, does that cancel? Yeah, so that's the second in our pair. It's going to cancel with the first. It's 2 to the right. So this one's going to cancel with this term here that we didn't write out. So let's cross these out as we go. The minus 5 over root 9, is that going to cancel? Yeah, so that cancels. We get cancellation all throughout here. We get to these. Maybe we need to look at these, maybe we don't. Sure. 5 over root n plus 2, does that cancel? Here. So that's the first in the pair. Cancels with the second, that's 2 to the left. Since we have the continuation, this is going to cancel with this one over here. That's gone. Minus 5 over root n plus 4, does that cancel? Yeah, it cancels. We see that canceling with this one here.
When you say 2 to the right, you're counting the parentheses.
Yeah, so pairs, the first pair, the second pair, yeah. 5 over root n plus 3 cancels with the one that's 2 to the left. So this cancels with this one right here. Minus 5 over root n plus 5 cancel? No. So that's the second in our, excuse me, the second in our pair cancels with the pair that's 2 to the right. There is nothing to the right on the second term. So this stays. And does this stay or does this cancel? So we've written that out to n terms. You know, n could be million, trillion, a billion, whatever. Those are the terms that remain. So therefore, the formula for the nth partial sum is those terms.
B 5 root 6.
This one. Minus this one. So that is our nth partial sum. I don't know if y'all have ran into any. There was definitely one in 10.3 that's nth partial sum. The computer wanted something very specific, which was the previous problem, number 13. If you haven't got there yet, it's fine. There's nothing I can do to fix it, though. It's just very particular.
Go back up.
Yeah.
Forgot the 5 root 6.
Okay. All right, so this nth partial sum, now to compute the series itself, which is an infinite sum, we just allow n to approach infinity. So let's just write this out. Sum from k equals 1 to infinity. Is it k equals 4, right? K equals 4.
Which is equal to 5 over root 5. That's 5 over root 6.
Yeah, right. So this is equal to the limit as as n approaches infinity. On our nth partial sum. You don't necessarily need to write all of this stuff down. Just trying to remind us what we're actually doing. Okay. So we see that as n goes to infinity, these last two terms approach 0. We just have 5 over root 5 plus 5 over root 6. As the sum of that series. Let's see. That's probably okay. It doesn't say to write it as a single fraction or anything. So. Any questions on that?
One thing I found very helpful about the telescoping is that I'll rewrite the k equals 1 to m. So I always remind us to stop. So that I'm to the left of m and to the right of 1 for a reference, right?
Yeah. Yeah, definitely with these, I don't know that you could determine what cancels without writing stuff down. I don't know, maybe you're just super awesome and can look at that and say, oh no, which terms remain. I mean, sometimes you can because they're, these two arguments, they're one's positive, one negative. They're 2 units apart from each other. So anyhow, yeah, it's definitely helpful to write the terms out. Any other questions? Yeah, Andrew.
Just real quick, and I'm sorry, could just be a second while I find it.
Sure.
Uh, 10.5, number 1. Sorry.
Yep.
Were you?
Yeah.
Ten 1, number 1, or 10. You said 10.5, number 1.
Yeah.
Okay.
Oh, okay.
There were some like that. I know.
Yeah, I had trouble simplifying it and figuring out what you would use for your D effect.
Okay, so since this one's a polynomial, I would just choose something that's comparable to it. So if I chose the series b sub k to compare to, well, what would we want to choose that as? So what's comparable to this?
1 over n squared.
Yeah.
You just use the first two. Right?
Yeah. So I mean, we just look at five n squared over into the fourth, or just n squared over into the fourth.
Okay,
Because this 5 we could factor out. It'd be the 5 out here. This would be n squared. This would be 1/5 n plus 1/5. It's not going to change the value of the series, or whether it converges or diverges, I should say. Change the value. Okay, so just 1 over n squared. Is that okay? Choosing that. And this is also the same procedure we went through when we chose if we were going to use a direct comparison. The direct comparison might be a little bit difficult to compare 1 over n squared to this polynomial to determine which one's larger or smaller, right? So that's why we use the limit comparison, because we don't have to make any sort of comparison between the two series that we're dealing with.
You know, piece of K for the
Yeah, and then we need to know does this series converge or diverge for the limit comparison test as well. So this is P series. Yeah. So it's because it's larger than 1, the power is larger than 1.
So would that mean the downward convergence is K?
Well, before we say anything about the original, we have to look at the ratio of the limit to see what is the limit finite, is the limit 0, or is the limit infinite? And then we'll make our conclusion. But we've seen hopefully enough of these examples where you know that this limit is going to be finite. But let's go through the process. So we compute L, limit as n goes to infinity. And then we take our A, this is our A sub k, divided by our B. Or times 1 over B. And then we're computing that limit. So what would that limit give us? Yeah. We just have n squared times all of this stuff. Our leading term here up top will be 5 n to the 4th, some other lesser terms, and then we have n to the 4th on the bottom.
so basically with that kind of polynomial, you ignore your lesser terms that are lesser than the leading term.
Right.
Pretty much, okay.
Yeah,
okay.
yeah.
That's what was throwing me off. You know, I'd always end up with an extra dash.
Oh, okay, yeah, right.
But that was trying to do the full foil rather than kind of ignoring. Anyways.
All right, yeah. Yeah, and then the other thing about the limit comparison is the limit is approaching infinity, or n is approaching infinity, so that dictates that we can just look at the dominant terms.
Because the example has you like it has you multiply obviously n squared over 1, and it has you write it all out, and then multiply the whole thing by n4.
Yeah.
And so you have to like do that, and you realize, oh, you're just really left with the top plus 0 and the bottom 1 plus 0 plus 0.
Right.
Just, like, I like what you did. You're just like, well, those don't even matter. It's just 5 n4 over n4. That's
Yeah.
way easier.
Way easier. It's way easier to look at dominant terms in the numerator and the denominator. In fact, we did that when we compute like the limit of something like 2 to the k plus 5 over 2 to the k, right? As k approaches infinity, we just look at the dominant term over the dominant term and we say that's 1. Instead of, their approach is more generic, and it is the approach that you take when you evaluate limits at infinity, because everything in theory is getting divided by this 2 to the k, where everything here is getting divided by n to the 4th. So that's why they say divide everything by n to the 4th, but it's the same result. Okay, so our limit in the limit comparison test is finite, and what does that mean?
That it does convert.
It does converge. When you have a finite non-zero limit, both of those series do the same thing. So we'll say, I don't know, do the same thing. I don't like that phrase.
probably might be scanned, figuring out how to do it.
Any questions on this example? Does that make sense? So choosing our comparison. What do we want that to be? I guess it could be anything really, but yeah. If we're gonna look at, you know, let's look at it like this. Just look at the leading terms initially, so that's okay. Yeah. So we see that's comparable. Yeah. 4 over square root of 4 over 25, which we can deal with. And then we have 1 over k squared. So that's comparable. Um, 2 over 5 times 1 over k. Since k is positive, starts at 1, goes to infinity, we don't have to worry about the absolute value. It's squared anyway, so you know that's what we could compare to. We could additionally just compare to 1 over k, because remember the constants do not affect convergence or divergence. So what do we know about 2 over 5k, or well, we can say that's comparable. What do we know about this series? It's divergent, yeah, it's the harmonic series diverges. Or you could view that as a p-series with p equal to 1. 1's not greater than 1, diverges. But again, we're thinking about this as equivalent to comparing or taking a limit with this function that does have, or a series that does have a square root in it. So we probably want to keep this thing in mind, this series in mind is equivalent to this series as far as convergence and divergence. So when we take the limit of this divided by this, you would have to some way get that k back into the root anyways. So let's just think of it with the root already present. That way we can just deal with everything under the root. Does that make sense? Here. Yeah, so let's write it out. Limit k approaching infinity.
You just do 1 over k squared then?
Yeah, right. 1 over k squared inside. But since we have this, we chose. Write this down before I tell. Okay, so that's our a. We want to divide by b or multiply by the reciprocal of b. So if we say that it's this, it's just a little bit more work involved to get that back into the radical to evaluate that limit. So we know that 1 over k series was comparable to this series.
Would it be k squared over 1 or multiplying by it?
Yeah, so it's going to be this thing here.
No, it would be the reciprocal.
Oh, yeah, my bad. We're dividing, this is dividing by b, and then multiply by 1 over b. Yeah. What?
You mean b over 1?
Yeah, what did I say?
1 over b.
I don't know, I'm confused now. I guess it depends on what context it was in. So we have to divide it by the, well, if we divide by that root, then we're gonna multiply by this here. So, yeah. I'm sorry, I'm not fully aware of what I said. Jargon was off, I apologize. Okay, so now then we can just absorb all of this into a single root. We'll just do that here. This is this times this over this root. So that we can pass the limit inside the root. What's the limit of our a times our 1 over b? Oh, we need to flip the 4 and the 25 too.
That's why we're.
Indeed. Well, and yeah, it wouldn't honestly, technically, we should have this, but it wouldn't affect. Did I just mess that up?
Yeah, it's a 25.
Yeah,
Yeah, the K-squared's on
Needs to go
top
up there
too.
Doesn't it?
Yeah. You better,
Oh my God.
better reciprocate that. Sorry, I'm human, I make mistakes. Please forgive me. There. Happy? All right. Inflappable teacher is making mistakes. Okay. So what is that limit?
If we wanted to, we could leave out that 25 over 4, right? Just to, like, get rid of more.
Yeah, you could, so we could have taken that out to k to the 5th. Even if this had a constant, we would still see that the limit is gonna be a non-zero finite number, however you arrange that. Assuming you arrange it correctly, not like I did. Does that make sense?
Yeah.
Root 1 over 8? Yeah, what do y'all think?
Yeah.
Oh, wait, no.
So the 25 is gone, 4 is gone, we've got a k squared, k to the 5th, so we've got. So let's maybe just take it one more step here.
Would it just be 1/2?
No, because these cancel.
Yeah, we got that 2 still.
Right, but k is approaching infinity, so we don't need to pay attention to that too. So limit's 1. What does that mean? It diverges, right? Finite limit that's not 0, the series do the same thing. So this series that was given does the same thing as this series, which is divergent series. I'll just write that up here. This diverges.
So, when you divide by b, why did you change? Why did you put the fraction under the square root? Like when you multiply by its reciprocal, whatever it's opposite.
Oh, so I want to take this right here and make it 1. So I'm going to multiply this by 25k squared over 4 inside the radical. So I'm going to do the same thing with this one. So this is all the square root of 1 that's just going up. Here's our a sub k, whatever that stuff was. makes sense. Any other questions with that?
Mine says it converges. Like the right answer when I did it was converges. Like my BUK is very different. You know, the problem is similar. It's the same thing. So I have like the root of 9k cubed over 16k with 4 plus new. And it wanted my BK to be 3 over 4k squared. And then it says that converges. I was like, I don't know how.
Square root.
Yeah, was it?
That's what I wanted my BK. No, it was just that. That was what my BK did. It says it converges. And I don't, it didn't really explain. So I was like, what?
But you had 9.
I had the root of 9k cubed over 16k to the 5th plus 3.
I think it's,
And all of it's square root, like the square root of all of it.
you just simplified that 9/16.
So but that's the way I wanted my piece of K. It just says my piece of K should be 3/4 K squared. And it converges.
Well, it's because he did this, it's basically the square root of 9k cubed over the square root of 9/16 or 16.
Well, wouldn't that leave you with 3k on top? Not 3.
Well, it's basically taking the square root of 9 and the square root of 16. So the square root of 9 is 3, square root of 16 is 4.
Yeah, I got that.
Those k's cancel out. 3k, k to the third cancels out. K to the fifth is 2k.
Yeah, you have to have the square root over that k squared for that to make sense.
The homework was very, the way it was when it done was like way.
Oh, I see. So you have choices. Okay, well, I mean, this is what we can compare to this one right here. Oh, that's all they wanted.
Yeah, I know. I didn't like that. I got the right answer. I just didn't know why. How
Are you sure it was this one?
Yeah.
Yeah.
Someone's getting a strong word.
I don't know.
How are you doing that?
So that's like.
Hold on. don't do it.
Actually, it looks like they're all B, no matter what. Oh, that one's not. Just kidding. Yeah, I have to look at that, Edward. Sorry. Okay, well, we went above and beyond. Any other homework questions?
Are we just gonna keep doing it and hoping that we catch up?
We really have no other choice.
No, once we just like take a break today.
Huh?
What if we just take a break today?
Probably violate some sort of labor law. or something.
We're not employees.
We pay to be here, don't we?
We're seasoned employees.
Well, I mean, we were pretty much done with 10.7 unless anybody had questions on. We have these last 2 examples to look at. We did the very last example. We skipped example 5 and example 6. Maybe just I'll remind you so let's state what test we should use to determine if it converges. Example 5. Yeah, it's got factorial in it, so a ratio test. So this converges. Maybe you can just use those as extra practice. Number 5 converges by the ratio test. 6, what test would be?
Root test.
Yeah, so we got to the kth power root test. The test converges. So
What are you looking at?
there's something like floating down the board. I couldn't tell if it was something up there or if it was actually on the board. So yeah, do you all have any questions on 10.7? Okay, then we'll start 11.1. So this is where we start to look at power series and specific types of power series, namely the Taylor series. So we'll see the definition of a power series, I believe, in the next section. But a power series is an infinite polynomial. Please k equals to 0 to infinity. And the structure of the polynomial is you have c sub k, which is just some coefficient in general times x minus a to the power of k. So the c's are coefficients. The c sub k indicates that they could well be different coefficients, right? It's not the same coefficient throughout. For instance, if k is equal to 2, then you have a second degree polynomial. If k equals 5, fifth degree polynomial, so forth. We'll come back to these in a moment, but just kind of to build this up, let's look at approximating functions with polynomials, specifically the linear approximation. So we're going to look at the linear approximation of the quadratic x squared minus 5 at x equals to 1. Yeah. So just as a reminder, when we look at the linear approximation is nothing more than the equation of the tangent line at that point. Or the equation of the tangent line. To find the linear approximation of the quadratic at x equals to 1, says write the equation of the tangent line to that function at the point 1, negative 4. Hopefully I can put this here. So we've got our y value plus the slope of the tangent line times x minus a. So that was our linear approximation. Notice this is directly just the same thing as us saying like y equals to y1 plus a slope times x minus x1. So just the equation of a line. It just, if you reference it in the textbook from section 4.6, the linear approximation anyways will take this form instead of the form we have written in black. So we find the derivative of our function, and then we evaluate our derivative at 1. Which gives us the slope of the tangent line on that function at that point. So we've got a point and a slope. That's all we need for the equation of the line. So the linear approximation is f of a plus f prime of a times x minus a. Yeah. So I'm gonna leave it like that because we'll see in a moment. It allows us to, I guess, fit that into the theorem that's presented. But yeah, it's 2x minus 6. So okay, so we found the linear approximation. I'm just gonna graph that on the computer instead of by hand there. There's our quadratic at the point 1, -4, and then there's the linear approximation. So the whole thing we're building up to is instead of using a line to approximate a function near a certain value or a point, we're going to start looking at polynomial approximations, like the quadratic, the cubic, etc., etc. So you see here what happens if we zoom in. The difference between the quadratic and our tangent line, 2x minus 6, you can't distinguish from it. Right? Clearly, as we zoom out, using the using the tangent line to approximate the quadratic for some of these x values is a terrible idea, right? Because this actual value is -4.9. Whereas on the linear function, it's -5.4. So that's what we're building up to. So are there any questions on that? Just using the tangent line to approximate function values. Now, notice as we get further and further out from the function, so let's say, some of these x values here, like once we're outside of this window for our x values, the approximation starts to get very bad. We do spend a lot of time talking about when we look at these series, for what values of x does that series actually make sense for? Okay, so Taylor polynomials, these are finite polynomials that are constructed to approximate the function. And the definition reads, so you've got some function f of x with all of its derivatives up to the nth derivative defined. This is the nth order Taylor polynomial. Sometimes it's nth degree. This depends on the textbook. They're usually used interchangeably. So the nth order or the nth degree Taylor polynomial for the given function with a center at A. So just think about the center as the analogy to the equation of the tangent line problem we just did. It's just the x value you construct the line at. So this center at an x value of A is where we choose to start constructing the polynomial about. We're building the polynomial around that point. So the nth order Taylor polynomial is just denoted p sub n. Has the property that it matches, blah, blah, blah. So here's the definition. The nth order Taylor polynomial p sub n centered at A is f of A plus f prime of A times x minus A. And you should recognize that at least this term, the first two terms are the linear approximation. But this goes even further and it says we're going to go out to the nth degree. Not the first.
How did we come up with that?
So we could once we start talking about differentiating and taking the derivative of these types of things, then the derivation or the justification that all of these conditions are actually true is pretty easy. I'm not sure if your textbook does that or not, but I would assume that they started looking at the equation of the tangent line as a good approximation. They said, well, how do we construct the quadratic approximation, and then the cubic, and then the quartic, etc. But that's just speculation. I'm not sure how it originated or where it originated. Yeah, so this is our linear approximation. So notice this Taylor, the format they take does fit into the notion of what we said was a power series. So here is a power series. A Taylor polynomial is an explicit type of power series where the coefficients, the c sub k's, are defined in a very specific way. So all of our coefficients are defined as the nth derivative evaluated at a, and again, a is just the center over k factorial. So I guess really the pattern to notice here is the derivative matches the factorial that it's over, matches the power that's on x minus a for all of those terms. Yeah.
How do you choose a value for determine where it is?
So it's typically given to you. Like I suppose in practice it would depend on what you're trying to approximate. Like if you have a I'm not sure about the higher order polynomials for this, but the linear approximation for this is 1/2 x plus 1/2 for x near a, or sorry, x near 0. So like if I were saying, well, forget that for a minute. If I said I wanted to approximate the square root of 0.01, for instance, then I might pick a value that's close to that. If not that value, a value that's close to it that I know I can take the square root of pretty easily.
So basically it just depends on what specifically you're trying to approximate.
Right, yeah. It really depends on the function of what you're trying to approximate, yeah. Okay, so this is a certain type of power series, a finite power series, where the coefficients are explicitly defined in that particular way. So you've got power series, kind of this global thing, and then you have like subsets of power series, like you've got Taylor series, there's Maclaurin series, there's all kinds of series. So we can just look at this as an nth degree polynomial approximation to a function at a particular location. So just our notation, p sub 1 of x is a first degree or order, so on and so forth. P sub 7, 7th degree or order. So the few examples we have in this section are just that, using a Taylor polynomial to approximate a given function. So, for example, e to the 4x, we could do that. E to the x is a little bit easier though. Start off with that. Oh, no, it's e to the x. So order 4, 4th degree. Some books will call these polynomials capital T. Just really depends on the author. I'll just write out the first couple of terms here so that we can have an idea of what we're trying to construct. So that's just directly from the definition. That's the fourth degree. We go up to the fourth derivative, x to the power of 4 over 4 factorial. Keep in mind it's the derivative evaluated at your center, which is given to us here to be a equals to 0. So we see that in order to actually compute what this polynomial looks like, we have to find the first, second, third, and fourth derivatives. And then you have to evaluate your first, second, third, and fourth derivative, and even the function at a equals to 0. Yeah, I'll write this right now. It's already on the board over here. So we're going to take our function and evaluate that at a equals to 0. In other words, f of 0 is e to the 0, which is 1.
What's the that equation of the sum of c to x minus a?
Yeah, that's for, we should note that. This is a power series in general. What this is saying is that the Taylor polynomial is this power series with these specific coefficients. So we could compactly write this. Sum from k equals 0 to 4. F k x minus a to the k all over k factorial. So we could write that compactly as that sum. So evaluated at a, and that's your c sub k right there. Is this piece right here. And so we've got to go out 4 derivatives. So fortunately, all the derivatives are the same. So we've got first derivative is e to the x, evaluated at 0, again, is 1. So are all of these. You see, depending on the function and the center, all of those coefficients could be different. Here, they just all happen to be 1. Evaluated at 0. And F. Let's just be clear here. This is f prime at 0. This is f double prime at 0. So forth. So that's really just giving us this part of our Taylor polynomial. When we construct that, we have to remember that those numbers are divided by their respective factorials, 2, 3, 4, whatever, and it's multiplied by x minus your center to the same power. Yes, let's write it out. This is p sub 4 of x. The first term is just the function evaluated at the center. So our first term is just f of a, which is 1. There's f of a plus f prime of a, we calculated that to be 1, times x minus a, x minus 0, to the first, all over 1 factorial. Maybe we'll just write that just to see. Okay, we move on to the second derivative. evaluated at 0 is 1 times x minus a squared all over 2 factorial. Third derivative at a times x minus a to the third over 3 factorial. And then our fourth term, just fitting it into this. Is everyone okay with what we're doing, or are there any questions?
If you just rewrite that whole series as x to the n plus 1 over n plus 1.
Yeah, in fact, yeah. Remember, this starts out at 0, though. So we've got 1, this is x to the first over 1 plus x. This is just x squared over 2 factorial. That's x cubed over 3 factorial. And that's x to the fourth over 4 factorial. So that's our fourth degree Taylor polynomial, approximating e to the x near 0.
That's the answer right there.
Yeah,
Let's simplify that.
no. That's our fourth degree polynomial. If you wanted to write it out in sigma notation, we would have the sum from k equals 0 to 4. And then our pattern here is x to the x to the k over k factorial, because this is k to the 0, k to the first, k to the second, k to the third, k to the fourth. Questions on that? This is really all it asks us to do.
If it was k over k factorial or k equals 0, would that be
There's 0 factorial something.
Yeah, so I might have misspoke. The only thing that's changing, here. Notice this index up to 4. The x's are still there, so it's what power of x are we dealing with? It's x to the k over k factorial.
My question is k or is 0 factorial 0?
No, 0 factorial is 1,
Okay.
1 factorial is 1, 2.
and 1 factorial is 1, 2.
Where's 0?
By definition.
I never cared enough to wonder why.
I mean, is it arbitrary or is it provable?
It's probably honestly came from a statistics probability thing when they're doing combinations and permutations. Like how many ways to pick a group of 3 if there are 0 people or something like that. I don't know. Maybe it's because of we're dealing with power series like this. By convention, it has to be 1. Otherwise, it doesn't work out. I'm not sure exactly the origin of that.
By definition of the answer. If someone made it so, and that's that.
Yeah, I know, and I always feel like that's just cop out, but I honestly don't know. I mean, it doesn't mean we shouldn't question things, right? Just because it's the way it is doesn't mean we shouldn't question it. I guess is my point.
We shouldn't or should question.
Should that be? Just because somebody says this is the way it is does not mean we should.
You might not like the answer.
So I know that's all it says, but let's just show kind of how this works in theory or in practice. Use the fourth degree Taylor polynomial to approximate, let's see, e to the 0.1. Now, before we actually go through that process, let's compare the graph of e to the x to our fourth degree Taylor polynomial. Yeah, 0.1.
Just like the second half of the question, or what?
Yeah, it's kind of like an addition to, question. We see the graph of e to the x here in purple, and then we see our Taylor polynomial here in black. So notice that we constructed it here. This was our center, and then we construct that polynomial basically around that point at 0, 1. I mean, we can start to see a little bit of divergence from the two, if you will. There is a difference. We're saying that as long as we're relatively close to this point where we constructed that polynomial, then the value of the polynomial versus the value of e to the x is relatively the same. Maybe a better way to write this. Okay, so that would be the linear approximation to e to the x at this point. Let me modify this. Go back to see what happens. So there's our quadratic, there's our second degree Taylor approximation, or polynomial rather. Third degree Taylor, fourth degree, fifth degree, 27th degree, 50th degree. But even over here, we start to see that divergence between the sum and the function become pretty insignificant. There is a difference. I don't know if this will let us get close enough to actually see that. It's such a good approximation that even this software is limited to show the actual difference. If we got out here, then we certainly start to see that. So we start to see a difference there. Anyhow,
So
that's
the higher you go up in degree,
yeah. The higher you go up in degree, the better it gets as an approximation to the function, which is what 11.2 and 11.3 deal with. Is writing a function as an infinite series.
You take it to infinity or b?
You take it to infinity. Yeah. They're only equal as the index approaches infinity. There's always an error or a remainder. Okay, so since this polynomial was an approximation to e to any input, all we're going to do is plug in 0.1 into p sub 4. We're going to evaluate p sub 4 at 0.1 rather. That polynomial is 1 plus x squared over 2 factorial plus x cubed. 3 factorial. X sub 4. In fact, your calculators use this method to compute values. So if you plug in e to the 0.1, your calculator might be using like a 12th or 20th degree Taylor polynomial to approximate that. But really, if you think about it, your calculator is only giving you like at most 10 digits worth of accuracy. So all the calculator programmers have to do is figure out how quickly or what the error is in this approximation, and then they just go out to the next term. So if they want to show you 10 decimal places, then maybe they just all have to sum to the 11th term or the 12th term to give an approximation that's accurate to 10 decimal places. Yeah, somebody has to program a calculator though. So somebody is smarter than the calculator. Not me, but definitely software engineers, computer programmers. Those people have to know like how to compute stuff. So you can plug that in, but what we get is 1.1. Zero 5 1.
That's exact, or?
This is the Taylor 708 33. That's our approximation using the fourth.
How far out do you want us to go?
I would say, yeah, it's just that this is a fairly decent approximation, so I wanted to go out just to see when we write down the actual value, we could see just how accurate this is. So the actual value of e to the 0.1 is 1.105. One 918. So we can see our approximation is off. All right, so if your calculator only displayed 1, 2, 3, 4, let's say 5 digits behind the decimal place, it doesn't really need to compute a whole lot to give you that level of accuracy. And the calculator can compute polynomials a lot more quickly than it compute logarithms and exponentials, rational functions, whatever. Yeah. So any questions on this?
I didn't have a calculator.
Yeah, because we could square 1 over 10, 1 over 100, 1 over 1,000. Be kind of a pain to do that division, but how about if we used the approximation use P sub 4 to approximate e to the 2.5. Again, our input here, we've already approximated the function e, so our input is just 2.5. So we're going to plug that into the Taylor for x. It gives us 2.8. Well, I'm gonna write it down. 10.85677 083. So there's our Taylor approximation of to e to the 2.5. The actual value of e to the 2.5 is 12.18249.
Are we so far off then?
So that's the question we want to answer. Why is that why is this approximation so far off?
Because what, our A, originally,
Right.
it's not close to that.
Yeah. So let's put this here. Y was P sub 4 X a bad approximation to e to the 2.5. So as Edward said, we constructed P sub 4 of X around the center A equals to 0, and 2.5, in parentheses, it's a relative term, is not near 0. Or near close enough to that value. Point 1 was, so we had a good approximation for e to the 0.1 because it's close to 0. 2.5 is not, so we have a bad approximation of e to the 2.5. Does that make sense?
Yeah.
So there's two ways we could clear this up. Two ways. So there's two ways to improve that. Anybody have any ideas?
Move A.
Move A, yeah. Pick a different A.
Then we have to recalculate.
Right. So if we move A, though, you have to reconfigure everything, because remember, this is the first, second derivatives, etc., evaluated at A, x minus A, right? So if we move A to 1, the polynomial is already totally different, because we have x to the 4th, x to the 3rd, x squared, etc. If our new center is 1, our terms are going to have x minus 1 squared, x minus 1 cubed, x minus 1 to the 4th. So you can pick an A that's closer to 2.5, but know that you'll have a completely different polynomial. What's another thing we might try?
Go to a higher degree.
Okay, use a higher degree. Okay, there is a downside to the second improvement. This is choosing a higher degree Taylor polynomial will not always work. We'll just put that in parentheses. As we'll see, as we progress through chapter 11, it really depends on what we'll talk about as the interval of convergence. Since we've already brought this up, just think about the interval of convergence to be the domain of the series. So it really depends on the domain of the series as to whether or not we get convergence as we go further and further out. Just think about the geometric series. It's only convergent for values in between 1 and -1, right? So if we said choose a higher order polynomial and take it out, what you'll eventually see is as we get past the interval from -1 to 1, that polynomial doesn't approximate the function 1 over 1 minus x anymore. is sort of outside the domain of the series.
What's the thing with this, is that the higher degree you go, the smaller the number of bits that you're adding onto it, so that you just have to go to such a high degree bit close to it, right?
Yeah. So the higher degrees we get, notice we also end up dividing by higher factorials. So those things do actually, depending on where x is, do actually get smaller and smaller. And that's important, right? If we want to represent a function as a series, it can't be a divergent series, because a divergent series would never approach anything in particular. A convergent series that approaches a number like 2, we could reconfigure to make it approach a certain function. So that's kind of the bigger picture. If we want these things to represent functions, they have to be convergent series. Otherwise, you don't have the series converging to a function. Okay. I think that's really all I wanted to say about that. Do y'all have any questions on that example? Oh, sorry about the time. Let's take a break.
That was not one of my problems.
Hey, you're only human.
So why am I asking you?
He also just.
I have done the same thing too on like a car ride. Everybody has like.
Oh, I thought it was.
Yeah. Like on a car ride, I've done the same thing. But not but to the point where everybody's surprised. Like, you know, somebody gets.
Okay. Y'all ready?
Ready.
Approximate cosine of 0.1 using a sixth order centered at 0. So here's the reference if you need it. We're gonna look at the function as cosine of x. And then over here we'll put our coefficients at a center equals to 0. To evaluate the function and its all six derivatives at a equals to 0. So cosine of 0 is 1. And let's just go ahead and find the derivatives. First derivative, negative sine. Second derivative, negative cosine. Third derivative, sine. And fourth derivative, fifth derivative. So here are repeating, some sort of getting offline there. And then sixth derivative. Negative cosine. So then we need to evaluate all of our derivatives at 0. And then we'll kind of see what happens here and maybe address whether that matches up with the cosine function or not. So notice anytime we have a sine, all of those coefficients are going to be 0. So the first derivative evaluated at 0 is 0. And so what that's going to do for our Taylor polynomial is just 0 out that term. So 0 there, we've got negative 1 here, 0, positive 1, 0, negative 1. So often you'll see these instructions as write out the first 4 non-zero terms of the Taylor polynomial, and certain ones, this is what happens. You get 0 as a term, so you've got to keep going, finding higher order derivatives. So notice that only gives us 1, 2, 3. It gives us basically 4 terms of the Taylor polynomial for cosine, even though we looked at the 6th derivative. All right, so our 6th order Taylor polynomial. And remember, this is approximating cosine of x. So cosine x is approximately the sixth order Taylor polynomial. Near zero. So we have our function value 1 plus our first derivative. Let me just write this term here. The troll. First derivative evaluated at a times x minus a, again 0, to the first over 1 factorial. I don't know if I can fit all of this in here. Our second, our third term, well, that got moved too. Still there. Okay, good enough. Third term from the second derivative, sorry,
Always consider minus x over x squared over 2.
x squared over 2 factorial, coming from the second derivative. Next term is 0 from the third derivative. Next term from our fourth derivative, coefficient is 1, x minus 0. Since that's coming from, that coefficient came from the fourth derivative, it's x minus 0 to the fourth over 4 factorial. Fifth term is 0. Sixth term coming from our sixth derivative, coefficient is negative 1, x minus 0 to the sixth.
Almost.
Write this here. And sixth derivative. So notice what terms we have. We have the zeroth, the second or the square, the fourth power, and the sixth power. So if we were going to describe cosine by a polynomial, since the cosine is an even function, it has symmetry with respect to the y-axis, it makes sense that our polynomial only consists of even degrees. Okay, so this p sub 6. If you just want to write it out all, cleanly instead of fitting it into this and then trying to simplify, I don't really care. So we have 1. We've got a minus x squared over 2 factorial.
X to the 4.
X to the 4 over 4 factorial minus x to the 6 over 6. And then we're approximating cosine of 0.1. Again, this is approximately cosine of x. And so the cosine of 0.1 is approximately p sub 6 at 0.1. Write it down here. 0.995 0.004. 1653. So that's really all the question asks us for. Let's write out the actual value just to compare, to have something to reference.
How do we enter main factorial?
Do you have a factorial button somewhere, maybe in the math menu? Not sure. Every calculator is a little different. If you don't have a factorial button, just type divided by 2 times 1, divided by 4 times 3 times 2, divided by 6 times 5 times 4 times 3 times 2. You just have the long factorial. The actual value, 0. The actual value is the same, exactly the same.
I calculated those 5.
5 decimal.
No, so in that 3 at the very end would be 5.
Oh, it does.
And that's because cosine,
Actually, no, it doesn't.
how cosine acts the function, just.
Because 0 is really close to 0.
Yeah. So we'd expect that to be a very good approximation. So that's the idea. Anybody have any questions? What we're doing? Okay, since we're pressed for time, I'm going to skip the last example. Just one thing to mention though, when we're approximating this function, we're thinking about this as the square root of x. And so when we approximate the square root of 1.05, our input into the polynomial is just 1.05. It's not the square root of 1.05. So we're saying that the square root of x is approximately the 3rd degree. So when we approximate this, that's our input. I guess if you want to try that as additional practice, you should come up with p sub 3 to be 1 plus a half times x minus 1. Notice here our center is at 1, so now we're going to have these x minus 1s to a power instead of like our other examples where it's just x to a power. Minus the 8th times x minus 1 squared plus a 16th times x minus 1 cubed. The factorials we just simplified. So like you would end up with like, this coefficient would be -1 4th over 2 factorial. We just called that 1/8. Yeah, that's fully simplified version. Do y'all have any questions on what we're doing there? It's easy enough.
So we're not going to go through this last page, or
What was the last page? Oh, that was it. Yeah, no.
Synopsis.
like a remainder though? No, not a remainder.
Oh yeah, I mean that's just saying that as we use the Taylor approximation to approximate f of x, as long as we're using a finite number, the function is equivalent to the polynomial, the Taylor polynomial plus its remainder. So there is some error in using a finite polynomial to approximate a function. So like our 4th degree that we use, there is error here
I see. So yeah, it's just
So it's just addressing like the error of that. And they're calling the remainder the error, whatever. Same thing. So the remainder is just the difference between the function and the polynomial. So here we see that difference right here. So we see that difference could also be approximated by a polynomial.
But what if you like took the integral of both of those to find remainder, the area between us? Would that make it
No, not necessarily, because then you would just be you're finding the area between the two functions, and it's completely different in how the error changes from one x value to the next. So if we do like the change like this, it doesn't really depend on the error. Yeah, and this was just e to the x with some 0th degree, first, second, and third degree Taylor polynomial. And then over here are the corresponding errors that we get. So third degree, in green here. We see that this third degree polynomial, it's only exact at 0 where we constructed the polynomial at. You know, outside of that, it starts to get a lot more noticeable, especially as we get around here. So this is R sub 3. So that the error between the axis and the function, R sub 3, is very insignificant. But then we see as we get further and further out, that remainder just keeps getting larger and larger. The error just keeps getting larger and larger. So one of the conditions that we don't talk about that has to be true is in order for that series to approximate or to equal a function, what has to happen to the remainder? Right, yeah, the remainder has to go to 0 in order for the series to be equal to the function. So we really don't do a whole lot with that, but I hope that's pretty intuitive. So if we rearrange this here, just to show you, if we rearrange this and say that f of x is the
remainder plus?
Yeah, we'll write it this way, polynomial, Taylor polynomial plus its remainder. Then in order for the function to equal this polynomial, as n approaches infinity, the remainder has to approach 0. Otherwise, you've got other stuff that's not involved with the function. It is also worth pointing out that what we have here with this cosine series, or this polynomial rather, is that it's alternating. So we have the error estimation for the remainder or the error in the alternating series. So like we wanted to approximate cosine to within a magnitude of like 10 to the negative 5th or 10 to the negative 12th, then we could do that. Since it's an alternating series, we know what the error or the remainder looks like. Do you have any questions on 11.1? So 11.2, we start to look at properties of power series. The power series is an infinite sum, 0 to infinity. We have these random coefficients, the c sub k's, times x minus a to the k. So in a power series, we could say that these c sub k's are usually random. Means there's really no specific order or formula for the coefficients. But the c sub k's in a Taylor polynomial are specific as the kth derivative evaluated at a times x minus a to the k over k factorial. So there is a specific formula or pattern to tailored polynomials coefficients.
I mean, over K factorial.
Yeah. So all of this over. I just kind of ran out of space there. So we saw finite polynomials in 11.1. Infinite polynomials are looked at here in 11.2, 3, and 4. So really the remainder of chapter 11 is dealing with infinite polynomials.
We don't do chapter 4 though.
Yeah, we do 11.4. Specifically in these last two sections, 11.3 and 11.4, is where we're using Taylor series, which is an infinite Taylor polynomial. And then infinite polynomials that have a center of a equals to 0, just for the jargon, are called the Maclaurin series. MAC LAURIN. So that's kind of an overview of what we're looking at moving forward. So let's look at the geometric series as a power series. We know the geometric series, remember, just in general was sum from k equals 0 to infinity, a to the a times r to the k. We're just going to look at r to the k with a equal to 1. So that's going to give us 1 plus r squared plus r cubed plus et cetera, et cetera. And we know, or we should remember, if the absolute value of r is less than 1, what does our geometric series, infinite geometric series sum to? A over 1 minus r. Here a is 1, so 1 over 1 minus r.
It's less than 1 though.
Yeah, the absolute value of r has to be less than 1. In other words, r is in this interval. So what if we did the same thing here, but we defined a function of x to be sum k equals 0 to infinity, not r to the k, but x to the k. So then what that looks like is 1 plus x squared, x cubed, etc. And we can say that's 1 over 1 minus x if the absolute value of x is less than 1. So now we start looking at these series that we've seen in chapter 10. We start to look at them with a variable, determine do they converge to a function, or what values of x do they converge to that function? So I hope that's pretty straightforward, just replacement of a variable with a fixed ratio.
a squared over one minus r, or is that?
If we had an a here,
Oh,
it would be a over 1 minus x.
a.
So, but what we're saying is, as long as x is in this interval -1 to 1, the function 1 over 1 minus x is this polynomial. So this rational function is this polynomial if, in other words, like we mentioned, and we'll state here when we get to this long definition, this thing right here, we're saying that this series, this infinite series or polynomial, is this function if this is true. This is the domain of the series, which consequently is the domain of that function if we want those two things to be the same. You'll see that we don't actually refer to it as the domain of the series. Below in this definition, we're going to refer to it as the interval of convergence. This series converges to that function for those x values in between 1 and -1. So as its name implies, you are looking at an interval. It is, and we'll see later as we go on, there's a certain number of cases. But you know, the interval from -1 to 1, an interval from -infinity to infinity, whatever that interval is the domain of that series. So since we did mention that, let's back up. A power series, defined here, random coefficients c sub k. They're real numbers. X is some variable. The c sub k is a coefficient of the power series where a is the center. Nothing's changed. If this were specifically the kth derivative at a over x minus a to the k factorial, then this would be a Taylor series, not just a generic power series. The set of all values of x for which the series converges is the interval of convergence. And then the radius of convergence is kind of from your center to one of those boundary points. So, you know, in general, what we're looking at is there's our center. We come up with some interval of convergence. Interval of convergence. And then the radius is just from the center to one of those points. So as long as we plug in these x values into that series, whatever the series is, it will equal a particular function. As soon as we get out of that interval, it's no longer equal to that function. Do you have any questions? So maybe you think about, well, I don't know, why would I want to represent a function as an infinite series, as an infinite polynomial? We've kind of seen one benefit as far as calculators go. Calculators are using that notion, and computer scientists probably use it for other reasons too. It's just a lot of times it's simpler to compute. If you take a differential equations class, you'll have to solve some differential equations by representing a function as an infinite series. And scientists use this too. If they have an involved function in their computations, like the sine of x, near 0, they're going to use x instead of sine x. Right? They're going to use their quadratic approximation to sine x near 0. So, I guess if you're interested, you could look in the back of the section, or just even search online. Probably get some very specific examples. So how are we going to test a given series is stated as follows. So here, we're now thinking of series as representing a function, and series now have the variable x involved with them, whereas previous chapter 10, it was just the k's and some operations. So basically 3 tests. If it's not geometric, we're defaulting back to the root or the ratio test. And those were valid for positive terms, and so that's why we have the absolute value built in. But having the absolute value built in also gave us the added benefit. The theorem from chapter 10 said that if a series converges absolutely, it converges. So if it converges under these conditions absolutely, then it converges. So the reminder for the conditions on both the root and the ratio test. The biggest thing to pay attention to are these 2 things here. The root and the ratio test are inconclusive if either the root or the ratio are identical to 1. So what that boils down to in practice, when we're testing these functions or these series, is that we have to test the endpoints. Endpoints of the interval of convergence. You got to manually test those. It's not absorbed or determined by these tests. So here's our function, the sum of x to the k over k factorial. It says find the interval and the radius of convergence. So if factorial is involved, which test? Ratio test. We're going to use the ratio test. And let's note here that a sub k is x to the k over k factorial, and a sub k plus 1 is x to the k plus 1 over k plus 1. Okay, so our ratio r limit as k approaches infinity. The absolute value of a sub k plus 1 divided by a sub k. There's a sub k plus 1. Divided by a sub k. Right, so we need to simplify this. Okay, so what is all that stuff simplify to?
X over 2.
Do y'all agree? I don't think so. That's x to the k times x to the first times k factorial on top. We have k plus 1 factorial, so we want to write that as k plus 1 times k factorial, so we can cancel the factorials. And then here's x to the k. Factorials go away, x to the k goes away, x to the first, x over k plus 1. So here, k is approaching infinity. There's no need for the absolute value around k plus 1. It's always a positive quantity. The limit only operates on k. So keeping that in mind as well. So that's equivalent to the limit as k approaches infinity, just the absolute value of x over k plus 1, which is just the absolute value of x times that limit as k approaches infinity of 1 over k plus 1. So it's 0, let's look at it like this. Let's look at it as this, that our ratio r is, no, absolute value of x times this limit times 0. So let's stick with that for a moment. In order for this series to converge, what has to be true for the ratio?
R has to be less than 0.
Yeah. So I'm going to go ahead and write that down for convergence. R has to be less than 1. So we have R equals to the absolute value of x times 0 has to be less than 1 for convergence.
Well, it could be any number then, right? X could be any number.
Right, yeah. So x, we see that our ratio here, it's always less than 1. No matter what x is, our ratio in this for this series is always less than 1. So any value of x you plug into that series will result in a convergent series. This is always true. It is any value of x will result in a convergent series. Yeah.
Does that necessitate that it converges absolutely?
Yeah, right, because we looked at the absolute value. So what we're saying is that this series converges absolutely for all values of x, which means it converges for all values of x. Remember, absolute convergence implies convergence.
How do you find the radius?
So what is the radius? What is the interval of convergence?
All real numbers?
It's all real numbers, yeah. So let's write that out. And think about this. The interval of convergence. The radius of convergence is what? Yeah, it's infinite, right? The length of the radius, if you will.
Wait, what's the close one?
Do what? Just same as above of
Oh,
convergence. Yeah, I just got it.
You go back a page and you said what that number line you had.
Yeah. Does anyone have any questions on what we've done? Does that all make sense or? Clarity? So back in 11.1, we looked at the fourth order Taylor polynomial for e to the x. Remember that?
So long ago.
So instead of stopping at the fourth degree or the fourth order, what happens if we continue in this way? What's the pattern here of the nth term, or the kth term rather?
X to the n over n.
Isn't that the series we just looked at? So the idea is like we haven't connected any dots to any functions. We're just kind of looking at them separately. Here's how you represent a function with a polynomial. Here's how you take a polynomial or a series rather and determine the interval and radius of convergence. And then we put it all together. So we say, hey, well, this thing we've already tested converges for all x. And then what we saw in 10.11.1 was that this is the series for e to the x. You know, I guess the connection again is not expected, but it's worth pointing out. It doesn't matter, no matter what value of x you plug in here, e to the 25th, that's the sum of 25 to the k over k factorial. These inputs match. This input here. So in other words, that series is e to the x for any value of x we choose. We've kind of showed those in pieces. But the idea is like construct a Taylor polynomial like this. Then once you see the pattern, then you write it out in closed form. And then you say, I wonder for what values of x does this series equal that function? And then that's when we do all of this stuff. Take the limit, blah, 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 then we come up with the domain. When what values of x does this equal this? Does that make sense? Second example. What test might be beneficial here? It's alternating. Notice we have x to the power of x minus 1 to the power of k and 2 to the power of k negative 1 to the power of k. We could certainly do a ratio test. No, that's the alternating series test. It is alternating. Remember, when the root or the ratio, we put the absolute value around, so it doesn't really matter that it's alternating. The ratio is okay to use here, it's fine, but I think the root test is easier, because if we take the kth root of all of this stuff, all of those powers of k go away. So we're computing the limit as k approaches infinity, the kth roots, or all of that to the kth power, 1 over k power.
Can we just make that with negative 1, 1?
Yeah, if you want. Don't forget your limit. I see a lot of people dropping that limit off in their computations. It's fine if you want to simplify all that stuff first, but at some point you need to come back to the limit, because that's not going to equal, like the last example, it's not going to equal 0 until you apply the limit at infinity. So just be careful with your notation. Okay, so we'll just apply the 1 over k, gets rid of all of those k's, and we have the absolute value of negative 1, the absolute value of 2. Clearly, we don't need the absolute value there. So that's ultimately what we're looking at after the root test. Limit as k approaches infinity, 1/2 times the absolute value of x minus 1.
So why did you put it to the power of 1 over there?
Because that's the kth root. Instead of writing out the kth root. Right, like the square root is the power of 1/2.
Oh,
Yeah. Are there any other questions on how we got where we? Right. Yep. And so this is that's our root. Notice this limit isn't really needed anymore. Oops, that's a root too. So again, for convergence, what has to be true about the root? Less than 1.
Less than one.
Yeah, less than 1.
See, that's where it's gonna get
Okay, so now we're back to solving inequalities. The absolute value of x is less than 1. Or sorry, the absolute value of x minus 1 times 1/2 is less than 1, and the absolute value is less than 2. So if you'll notice that right there gives us our radius of convergence. Our radius of convergence is 2. We'll have to pick back up on Thursday here with this example. Before we leave, do y'all have any questions?
how would you solve for x right there?
So we drop the absolute value bar. That's equivalent to saying, x minus 1 is less than 2, but larger than negative 2. Which means that x is less than 3, but greater than negative 1. So there's the interval of convergence. You just have to remember that from college algebra, the absolute value of x minus a less than a number, that just means that x minus a is less than the number, but greater than the negative number.
Yeah, we start.
The brain.